let P be projection map on Banach space B then M, which is image of P, N kernel of P or the null space of P are closed linear subspaces of B. Proof. M and N are subspaces of Banach space B. It's an easy to check. The kernel is always a space, and if you take any two points over here, if you take U and V, U is the preimage, V is the preimage, so you add two preimage. So, and since P is a linear map, so suppose P of X is equal to U, P of Y is equal to V, so P of X plus P of Y is equal to U plus V, so P of X plus Y is U plus V. So the point is that X plus Y, so the sum of elements is also in image of P. And if you take any scalar, then scalar times that element, it's again in here. So image and the kernel, they are subspaces. The point is that what we are interested is that we want to prove that it's in fact a closed subspace. So how do we show that it's a closed subspace? So first look at the following fact. M is image of P. This is also the kernel of I minus P. And N is itself is kernel of P. So P is a linear, I minus P is also linear, we have shown, and this is also projection. P is a projection on image of P. I minus P is a projection on N. This is what the image of I minus P. So I minus P is a projection on N, and P is a projection on M. If you take a sequence, if you look at this object over here, now this is a closed set. Why this is a closed set? That because it's B is a non-linear space, it's having a metric on it. If you take a sequence, suppose xn, n going from 1 to infinity, is a sequence in a what space? Sequence in n, and suppose is a sequence in n, and that xn is converging to x. In other words, what we are taking is that let x belonging to n bar. Then there exists a sequence which is converging because of the metric topology and so on. So this is a sequence which is converging. So what happens to, since P is given, P is a projection on a Banach space, so algebraic projection, so P square equal to P, as well as P is given to be continuous. P is continuous means what? If you have this one, then P of xn, the sequence, this converges to P of x. But each of this xn is in n kernel of P. So P of x1, P of x2, P of x3, each of them is 0. So 0, 0, 0 converges to what? P of x. So this implies what? Since in a metric space, the convergence is, it's a Hausdorff space, unique limit. So P of x is equal to 0. If P of x is equal to 0, that means that x belongs to the kernel of P. So if x is in n bar, that implies that x belongs to n. As you can clearly see that M is image of P, M is also the kernel of some linear map, linear, continuous, and this is also projection. So what does this mean? This means that M is also what kind of space? A closed linear space. If you have a projection space, projection map, then the corresponding image space and the kernel space, both of them are what? Both of them are closed linear subspaces. The converse, we'll try to see what happens to the converse, that you start with the two closed linear space, and the space is a sum, is a direct sum rather, that is every element is a unique linear combination. Then you can define projection on some space, and you can get a projection map out of it. So before that, let's try to prove a proposition about Banach spaces. Some proposition. If suppose B is given to be a Banach space, and so there is a norm on B. So this is a norm on B. Okay. And B is also further given as that it's a direct sum of two, maybe say M direct sum N. So what does this mean? This means that if you take any Z belonging to B, there exists unique there exist unique X and Y belonging to, so let's write this thing as more properly, unique X belonging to M, Y belonging to N, such that Z is equal to X plus Y. Okay. So the moment you have this thing, then we put a norm on this thing, the one norm. The one norm is nothing but norm of X plus norm of Y. Norm of X plus norm of Y, then this with respect to this norm. So X is object in M, M itself is a subset of B. These are subspaces and so on. This is also subspace of B. So an intersection is empty. What does this mean is this one, and M intersection N is also not empty, rather, and its subspace is 0. Intersection is trivial as a subspace. They intersect only in this singleton 0. Okay. So this is the relation. Then the claim is that if B is a Banach, the space B with one norm is Banach space. So let's call this space as a B dash. So to distinguish, so B and B dash. So B is with respect to this norm. B dash is also B as a set. So B is equal to B dash. That is what we want to as a set. And there is a one norm on this thing. Okay. And what we are trying to show is that if B is Banach with respect to this norm, B is also Banach with respect to the one norm. Proof. So every element, so if you take any typical element in B, so if Z belongs to B, there exists what? Unique X and Y. So that what happens? Z is equal to X plus Y. Okay. So norm of, let's check that. Norm of that Y is non-negative. Since this is norm X plus norm Y, the first condition is that, so this is greater than equal to 0 plus 0. This is nothing but, so this clearly implies that norm of Z is greater than equal to 0. So the norm is non-negative. Z is any element in B. If second norm of Z1 is equal to 0, this implies that norm of X plus norm of Y, this is 0. Now these two terms are real numbers. So this implies that norm of X is equal to 0 and norm of Y, this is equal to 0. Because it's a non-negative terms and sum of two non-negative terms is 0, then each of the term has to be 0. Both of them are non-negative. They do not cancel it out by subtraction and so on. So, but this is in B. By definition, X is in M, so X is in B, Y is in N, so Y is in B. So this implies that X is the origin, Y is the origin, so X is 0 and Y is 0. So this clearly implies that Z is 0 plus 0, thereby implying Z is 0. So this takes care of what? The second property. The first property with two parts. The second property is of the norm is what? The triangle inequality. Suppose I have two elements Z and Z dash. Its norm would be what? So Z is X plus Y, and this would be X dash plus Y dash. This would be norm of X plus X dash, so the one norm of this thing over here, plus norm of Y plus Y dash. What is norm of X plus X dash? This is less than equal to norm of x plus norm of x dash. What is this thing? Plus norm of y plus norm of y dash. What is this one? The sum of these two terms is nothing but norm z, one norm, and these two terms over here, norm of z dash, one norm of this thing. So the triangle inequality is there. And the third object is what? Norm of alpha z would be what? Norm of alpha x plus norm of alpha y, one norm. This is nothing but mod of alpha times norm x plus mod of alpha times norm y. What is common here? Mod of alpha, norm x plus norm y. And hence this is nothing but mod of alpha times what norm? One norm of z. So what do we get from here? So it's a non-linear space we have shown. So B dash is a non-linear space with respect to one norm. Now let's show that in fact it's a Banach space. So every Cauchy sequence in B dash that converges. Now, claim every Cauchy sequence in B dash converges. Let's take a sequence. Maybe say suppose Zn is a sequence n going from 1 to infinity in B dash, and it is given to be what? To be Cauchy sequence. So given epsilon greater than 0, there exists n belonging to set of natural number such that for all m and n greater than or equal to n, what happens is that norm of Zm minus Zn, this is the one norm, strictly less than epsilon. But the definition of one norm, what do we have? This is nothing but xm, so it would be xm minus xn plus norm of ym minus yn. This is less than epsilon. So sum of non-negative terms. So this implies clearly that norm of xm minus xn, this is less than epsilon, and norm of ym minus yn, this is also less than epsilon. Yn, this is less than, but this is a sequence. So what happens? So the xn, n going from 1 to infinity, what does this mean? So this is a sequence if you look at correspondingly, and this is sequence in B, this is sequence in also B. Both of them are Cauchy sequence. We have found a stage after that xm minus xn is less than epsilon. If this is a Cauchy sequence, we have a limit, and this converges to x in B, which is B dash, but the norm is different. So what happens is that this converges to y. So what would happen is that, so the z, if you consider z as x plus y, it's easy to see that the sequence Zm or Zn converges to z, because xn minus x, norm of xn minus x, this tends to 0, as n tends to infinity, yn minus y, this tends to 0, and so we have this one. Is that so? B with respect to one norm is complete metric space. And it's a, this is the case, complete metric space. So why it is easy to see that? Because we see that by the one norm. So how the one norm comes into the picture is that the one norm is norm of x plus norm of y. If you observe this thing, the Cauchiness of this thing, implies that this is Cauchy and this is Cauchy. And suppose if this converges, then correspondingly you can find this thing. So we use this fact to prove what that if P is so P as a projection, so given two closed linear spaces, which sum, if you take the direct sum of them, which is the whole space, then in fact is what? The P is a projection on the space. So it's a linear, continuous, and P square equal to P. Proposition. Let B Banach space M N closed linear subspaces such that B is M direct sum N. Okay. What does this mean is that M intersection N as a subspace is singleton 0, and every element of B can be written as a unique linear combination of element in M in N. So if Z belongs to B, there exists a unique X and Y belong X in M, Y is in N, rather respectively you can write X is in M, Y in N, such that Z is equal to X plus Y. Then the map, so if you take any Z, so this is a Z, so P of Z is equal to X is a projection map. Projection map onto M. That is, P is linear and continuous. So projection, what does it mean? Is that it's idempotent also. So given P projection on a Banach space, we are able to find two closed linear subspaces. Now, given two closed linear subspaces, and the space is a direct sum of those two closed linear subspaces, then we can project. We can have a projection map onto M. So if P is a projection on M, if we show that I minus P would be a projection on N. So let's try to prove this thing. So P, so we'll use the thing is that one norm and so on, what we have proved the previous proposition. If B is a Banach, we have shown that B dash is also Banach. So what is B dash? B dash as a set is equal to B as a set, but the norm, the one norm on this thing. Okay. So P as a map from B to B dash. So what it would be? So if you take any Z in B, then what do we have? Any Z belonging to B, there exists a unique X and Y. Is that Z is equal to what? X plus Y. P of Z is equal to X. So the norm of P of Z is norm of X, which is less than equal to norm of X adding a non-negative term, but which is this object here is nothing but the one norm of Z. So what do we have? Norm of PZ is less than equal to one norm of this thing. Okay. Rather, what I would say is that here it should be B dash to B. Okay. Both of them, so both B and B dash are set B, but here we will use the one norm. So P of Z, okay, so Z is there, Z goes to P of Z. So here there is this norm on this space, and there is, this is the one norm on this thing. So on the left hand side, so claim is that P is continuous. So if you take any sequence, Zn is a sequence, converges to Z, okay, in with respect to in B dash, then what happens? If Zn converges to Z, then norm of Zn minus Z, so it would be P of Zn minus Z. So this clearly implies that P of Zn converges to P of Z in B. Something, if you take a sequence in B dash convergent, then the image is also convergent, because if Zn minus Z is less than epsilon, that would imply P of Zn minus P of Z, that is less than epsilon. So P is clearly continuous. The point is that we have shown that P is continuous. Okay. And then one can easily check the algebraic nature of P of Z. So P of Z is this thing, and then X is nothing but this is X plus 0 could be written as a digression from here. Now the point is that what would be P square of Z? It would be, if you apply again P, X plus 0, it would be just P of X. But P of X is what? Is P of Z. P of X is, so P of X would be P square of Z. Okay. So P of Z is P of X. So P square of Z is P of X. P of X is P of Z. Just a minute. We'll have what over. Just a minute. For algebraic this thing. Z is equal to X plus Y. So P of Z is P of X, and P of Y would be what? Since it's a projection, this would be 0. So P of Z is P of X. So P square of Z is P square of X. Okay. Which is equal to. So the point is that in algebraic projection, X is equal to P of X. So if you look at M, we have seen the following fact. If we look at M, which is the image space of P, the algebraic projection, we have proved the continuity with respect to B dash. We need to show with respect to B. So, but P of X is equal to X. If it is algebraic projection with respect to M, so what do we get is that what is X? So if you apply this thing, so this is P of X, which is P of Z. So that clearly implies that P square of Z is P of Z for all Z belonging to B. So let's show that P, in fact, not only is that it's a continuous with respect to this one. So we'll consider the following map. So we'll consider the following case. We have B dash to B. There is a projection map B. B dash to B. Consider the identity map. So what do we have over here? Z is going to what? Z in this case. Z is what? X plus Y. The norm of Z, which is on the right hand side, norm of X plus Y, which is less than equal to norm X plus norm Y. This term over here is the one norm of Z. So what do we have? So if Zn is a sequence in B dash such that Zn converges to Z in B dash, that is its convergence with respect to one norm, Zn minus Z. Okay, so let's say we'll use some another word, maybe Z dash. Zn, so this is a sequence Zn dash which is converging to Zn dash, and with respect to the one norm it is converging. So clearly Zn minus Z, this would be less than equal to norm of Zn dash 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 dash, this one. If this as n tends to infinity, if this is going to 0, this is going to 0. In other words, what we have just shown, I is what kind of map? It's a continuous. I is clearly linear map. It's clearly 1 1 and clearly onto. So the proposition before this one, projections, what we were talking about, just the open mapping theorem, if you allow. So if you have a 1 1 onto map which is continuous, then it is in fact a homeomorphism between two Banach spaces. So this is a Banach space, this is a Banach space, so it's a homeomorphism. In other words, the I inverse map is also continuous. So I inverse is continuous. So what can be done from here is that and the I inverse map is nothing but I is the identity mapping as a map Z going to Z. So what do we have is that you have a B over here, B dash over here, and so the identity map over here and P, this is continuous, this is continuous. So the composition P composed I, this is continuous, and P composed I square would be same thing as what? It would be just P square, but P square we have shown that it is just P. So what we get is that this proves that so the P is continuous from B dash to B, so P is continuous from B to B also, which is P composed I. So we have shown that given two closed linear subspaces, then if the space is a direct sum of M and N, then we can define a projection map on a Banach space. So what are the things to be noted? Algebraic projection. What is an algebraic projection? An algebraic projection is simply a map from a vector space to a vector space. V is a vector space, is that P square is equal to P, and it is requirement is that P is just linear. In a Banach space or a non-linear spaces, what we are interested is that P is a map from B to B. It should be idempotent, linear, and continuous. So that is what we require. So P is a map, then it produces what? Two subspaces and so on. So given two closed linear subspaces, we can and if for B, there is another condition. If for B is M direct sum N, then so the continuity and this sum is important. It may happen that on a Banach space there may be closed linear subspaces, but the point is that it may not add up to the whole space B. So the existence of such M and N whose direct sum is B happens on a space which is known as a Hilbert space. Later we'll see that. So there is an additional property with P which is satisfied on a Hilbert space, which is the inner product space. Then you have that the moment you have projections on Hilbert spaces, you are able to decompose the space as M direct sum N. The algebraic projection, if it is not continuous, then there are several. So the image space is there, range space is there, but it may not be a closed. And even if it is closed, it may not be adding up to what? The whole space B. So on a Hilbert space, we will have this thing. But direct sum exists of the whole space.